Okay, so let's talk about directional derivatives. A directional derivative is just a derivative whenever you're facing a specific direction, and that direction is defined by a unit vector. And you'll see this in your practice problems that I'm going to do right now. But I'm going to show you guys how to solve for directional derivatives. First function we'll be covering is x squared plus y squared at point. So we're finding the directional derivative at point 1, 2 in the direction of this unit vector 3/5, comma 4/5. So first thing we have to do, we have to find something called the gradient, and the gradient is going to be represented with this upside down triangle called nabla. You don't have to know the name, just know that this stands for the gradient. And what the gradient is the f of x partial, comma f of y partial, and this will be the function for the gradient. So how do we find the gradient? Well, the gradient here is, let's set this up. So we have to find the x partial for this. So the x partial for this function is 2x because we treat y as a constant, and the y partial for this function is 2y because we treat x as a constant. Now that we have that, our gradient in this case is 2x comma 2y. And with this gradient, you can plug in your point values. So we'll plug in the points in the gradient. And what we get is f of x, nabla f. So we plug in 1 for x. Since there's no 2 value inside of this function, we'll just plug in for 1x. We get 2. And if we plug in 2y, we plug in 2 into 2y, we get 4. So this is our gradient here. And this gradient, in this case, will be something that we'll use. So once you find the gradient here, treat this as a vector. And with this vector, you dot product with the unit vector. So this is a unit vector that points in the direction that we're trying to find the derivative of. And keep in mind, the unit vector's magnitude is always 1. So once we have the gradient, we just treat this as a vector and we dot product it with the directional derivative. And once you find the dot product of this, that will be the slope of your directional derivative. So let's go ahead and do that. 2 times 3 over 5 plus 4 times 4 over 5, which is equal to 6 over 5 plus 16 over 5, which is just equal to 22 over 5. So that is our slope in the direction 3 over 5, 4 over 5 at point 1, 2. Next function will be defined by e to the power of x times sine to the power of y. At point pi over 4 in the direction negative 2 over square root of 2 over 2 square root of 2 over 2. So this is the point that we're covering, and this is the unit vector that we are finding the direction of the derivative in. So the first thing we have to do, we have to find the gradient. Let's try better. And the gradient, again, is just the f partial, the x partial, comma, the y partial. So it's just two different functions. And once you plug in the points into this function here, you get the gradient vector. So the gradient is, we have to find the f of x partial and f of y partial. So the f of x partial here, since y is treated as a constant, the f of x partial is just sine y, e to the x times sine y, matter of fact. And the y partial is e to the x cosine of y. So now that we have this, what do? Well, you can plug in e to the x sine of y, and e to the x cosine of y. And this is our gradient here. But we have to plug in these values as well. So once we plug in, these values, once we plug in 0 and square root of 4, pi over 4, not square root, just pi over 4, you get e to the power of 0, which is just 1. So it's 1 times sine of pi over 4, since this is the y value and this is the x value in these points. So pi over 4 inside of sine will be our square root of 2 over 2. If we plug in 0 to e to the power of x as well, this turns into 1, and cosine into with pi over 4 is just square root of 2 over 2. So this is our vector. This is our gradient vector. And once we find this gradient vector, again, you just dot product with the directional derivative. And coincidentally, in this case, the directional derivative is quite literally the same thing as the point that we found. So if you multiply these, you get square root of 2 over 2. You get 1/2 when you multiply these two. If you multiply these two, you get positive 1/2. Therefore, our directional derivative at 0, pi over 4, is 0. The next function will be defined by ln of x squared plus y squared. We're solving for the directional derivative at point 1, 1 in the direction of square root of 3 over 2, 1/2. So this is our unit vector for the direction. This is our point, and this is our function. So again, we have to find the gradient. And the gradient will be, let's write this with proper notation. The gradient is f of x, f of y. So let's find f of x. And f of x is, so x partial, we treat y as a constant, and we get x squared over x squared plus y squared. And let's get some more space here. Okay. And we treat x as a constant now. And I just noticed my mistake. This is 2x up here. And our y partial is 2y over x squared plus y squared. And we got the 2x and the 2y using chain rule. Now, what do we do next? Well, we have to plug in the values of 1 and 1 for this. So if we do f of x 1, 1 and f of y 1, 1, you get 2 over 2, which is just equal to 1. And that's the same thing for y. So our gradient vector is 1, 1. And let's put that down here. 1, 1 got from the values of this, where we plugged in the point values. After that, again, do a dot product with the directional derivative. And once you find that, the scalar value that you get will be the derivative of the at that point, the directional derivative at point P. And this is our answer in this case. Moving on, our next function will be defined by x to the power of 3 plus 3xy squared. And we're trying to find the directional derivative at point 2, 1. And our direction this time isn't a unit vector. Our directional derivative this time will be a vector. But it's still a directional derivative. So you need to turn this direction into a unit vector. Let's start this off with finding the gradient. So the gradient is defined as the f partial with the y partial. The x partial with the y partial. And the x partial, in this case, is 3x squared using chain rule and x, and 3y squared using power rule, not chain rule for this, this is power rule, using power rule on this as well. Because we treat y as a coefficient, since it's a constant, this x just goes away when we find the derivative, and y squared stays the same. So for f of y, this x to the cubed is a constant, so it turns into 0. So all we do is find the y partial for this part right here. The y partial for this part using power rule is 6xy. Now that we have that, we must plug in our point values. And if you plug in 2 and 1 for the x and y values here into the x partial, you get something like 12 plus 3, which is equal to 15. And if you plug in 2 and 1 here, you get 12. Once you have the gradient values, so you have the gradient 15, 12, this will be treated as a vector. And you dot product this vector with the unit vector of the directional derivative. So you can't dot product with 4, 3. You have to dot product with the unit vector of 4, 3. And what is that? Well, in order to find the unit vector of some vector, you have to find the magnitude of the vector and divide the magnitude by all the components. So what do we get back? We get this. So as you saw here, I divided the magnitude of the unit vector by all the components of this vector, and this right here is our unit vector for the directional derivative. So all we have to do is solve this part right here. So you dot product with the unit vector of the directional derivative. And once we have this, we have 15 times, so 15 times 4 over 5 plus 12 times 3 over 5. This 5 needs to be fixed. And then this is, what is this, times 3? It's 12, right? Plus 12 times 3 over 5, which is 36 over 5. And once you get some constant value, I mean, like, you could just leave it at that. You could honestly just leave the answer at this. But this probably looks better. Finally, we're on the last problem. No offense. I wrote 5. The last function will be defined as sine of xy plus x squared e to the power of y. And we're finding the directional derivative at point 1, 0 in the direction 1, negative square root of 3. So in this case, again, we don't have a unit vector. This does not have a magnitude of 1. So you need to find the unit vector later on in this problem. First thing we have to do, always find the gradient. And the gradient, again, is defined by the x partial, comma, with the y partial, paired with the y partial. Let's go ahead and find the x partial. So the x partial in this case would be, since x is in this sine function, we have to chain it as well. If we chain it, you get cosine of xy times y. And since e to the y is treated as a constant, since we're deriving with respect to x, all you do is use power rule on x squared, and this is what you get. How about for the y partial? Well, for the y partial, again, use chain rule, and since the y is within the sine function, you can turn it to cosine. The next part, x is treated as a constant, so it's just treated as a coefficient. But when you derive anything to the power of e, it stays the same. So this part just stays the same. Now we have to plug in our values. And our values are 1 and 0, respectively x and y. So we plug in 0 for y, this just zeroes out the entire thing. So we get 0. If we plug in 1 here and we plug in 0 here, just 2 times 1 times, well, e to the power of 0 is 1. So this is 2 times 1 times 1. So it's just 2. How about for 1, 0 and the y partial? We plug in 1 for the x value. When we plug in 0 in cosine, all this is just cosine of 0 multiplied by 1. But when you multiply anything by 1, it just stays the same, so we can just remove the 1. And if we put in 1 here, we get 1 times 1. So it's just plus 1. And cosine of 0 is 1. So it's just 1 plus 1 equals 2. So our gradient is 2, 2. Dotted with this directional derivative. Well, this directional derivative is not a unit vector. This does not have a magnitude of 1, so we have to find it. How do you do that? Find the magnitude of the vector. Let's fix this. Find the magnitude of this. The magnitude of this is equal to the square root of 4, which is equal to 2. So the magnitude of this vector is 2. If we just divide all the components by 2, you get 1 half, comma, square root of 3 over 2. And this is our unit vector here. So if we have this, we dot product the gradient with the unit vector, and then you get your directional derivative. 2 times 1 half is just 2 times 1 half is just 1, but we'll put that in there, and we get negative 3 over 2 times 2. Let's make space for the rest of this problem. So this is just equal to 1 plus, technically minus square root of 3. And that is our directional derivative. So if you have any questions, put it down in the comment section. Hope you guys learned something.